All right. I guess we can start here. Oh, I see. Ms. Mbozi, do you want to help us by please? Can you confirm if you can hear me just fine, please, so that we start our lecture. You're breaking there. I couldn't get what you said. Yes, you saying? Yeah, I don't know about that. Your connection, I don't know if it's my connection or your connection. Milna, are you able to hear me just fine? Hello? Okay, could you just okay, thanks Jillian, Miss Mbozi, thanks. Um, so we're gonna continue our discussion, right? A reminder that we started looking at so-called interaction diagrams, right? And I think it's important for us to be reminded that the UML specification has a series of models, right? If you look at that specification document from the object management group, you notice that these UML artifacts, UML models or diagrams can be categorized, right, into certain stratas. And what we said was that we're going to look at example models that fall within these different categories. So we took time to look at so-called, I want to say this is like an interaction diagram called use case diagrams. We looked at structural models or structural diagrams, specifically class diagrams. And then we're looking at, I want to argue this is like a behavioral kind of model, really, but they're also classified as interaction diagrams, so-called sequence diagrams, right? And so our discussion of sequence diagrams got us to a stage where we realized that they're essentially an extension of use case diagrams, right? Whereas use case diagrams will model the interactions of users with the system from the perspective of specific tasks that they'll be performing with the system. In other words, the specific objectives. We discovered that sequence diagrams will extend use case diagrams by way of explicitly helping model the interactions that take place. So for instance, if we say we have a user who is going to log in, in a sequence diagram, or we have a user who's going to log in. A sequence diagram will, or maybe we can use this example, a user who's going to ingest a digital object. Using a sequence diagram, all we are doing is we are specifying the user as using a stick figure here as an actor, and then we draw an association, right, to an oval shape or an ellipse that will represent that use case called object ingestion. But we realize that when we're building software, that's not sufficient, right? You just can't tell a programmer to say build a system that will have a feature to enable somebody to upload or to ingest a document. The question is going to be how exactly should this ingestion work, right? So enter the world of sequence diagrams where you model the interactions as they take place. So you realize that this use case code or the association between an actor called postgraduate student and the use case called digital object ingestion or ingest digital object will manifest itself like what you're seeing on the screen, right? We realize that the actor is going to initially interact with the digital object, and then there'll be a cascade effect, right? So the digital object then will end up, evoking a method that is perhaps contained in the metadata object or metadata class, and then also evoke a method contained in the bitstream class or something like that, right? So we are modeling interactions. So something that's similar to this. And really, when we started our discussion, or at some point during our discussion last time we met, we realized that the notation is actually a bit complex, right? So there are specific elements or components associated with a sequence diagram, so things that make up a so-called sequence diagram. And specifically, we said that for us to come up with something like this is like a complete sequence diagram, we have got to first of all take into account that there are various aspects or elements associated with use case diagram, starting from the so-called name, right? Interaction name. The interaction name is represented as a rectangle, typically placed on the top left side of the diagram, the sequence diagram itself. Top left rather, not right, top left, if you notice SD and the name of the interaction. Typically, by convention or depending on the sort of tool you are using, you prefix it with an SD, sequence diagram, right? Space and then the name of the interaction itself. Okay? And we discussed guidelines on how you go about naming these interactions. Something else we discussed was this notion of so-called participants, right? Because if we are saying that we are modeling interactions, the obvious question to ask is, what entities are interacting with each other? Well, it's actors and objects, right? Or objects. And the interaction manifests itself through evocation of messages, or message passing in essence. Right? So we see here that the participants who comprise actors, which can be represented as stick figures if you look at the red bounding box, right? This actor, if you remember our discussion of use cases, doesn't necessarily have to be a normal human user. It could be a third-party system. It could be a piece of hardware, for instance. Okay? And then we have our so-called objects. Now, these objects will represent, if you remember our discussion of classes, these are like instances of those classes. Okay? So in this particular case, we are saying at some point there's going to be a situation where the digital object class is going to evoke a method contained in the metadata class, right? And we see this manifest itself through this message evocation of the message specify object metadata or something like that. In terms of the syntax, we see really that, again, just to rub it in, your objects represent instances of a class. Your class is a blueprint, if you remember, your 2010. And these objects are represented as rectangular shapes with the name of the class, or the name of the object rather, inscribed within the rectangle. So this can be represented as an anonymous class, which is the case here. You just have a full colon followed by the name of the class. So you're saying this is an anonymous object, or you can give it an explicit object name. Observe, if you come here, you have a P full colon followed by the name of the class, right? This is not an anonymous object here. It's like you're saying there's an object P here, right? Of type patient info or something like that. Okay, so we had a discussion of this, which was quite interesting. I don't know how many of you were following through with what we were discussing, right? And then there was a discussion of so-called lifelines, right? Now we said that the lifelines are typically represented using dotted or dashed vertical line, right? They'll represent a participant ideally. So in essence, what the point we're trying to put across here is that the participant is just not represented in isolation. They have an associated lifeline. The way you specify, observe, the way you specify a participant is it would be like an object or an actor with an associated lifeline. So if you go to draw.io, what you begin to notice is when you're putting together, yeah, I don't know what's happening here. I should have just opened. I don't know if this thing is recent. Thank you. Beautiful. But why? What? This thing doesn't even have. Okay. If you notice, if I wanted to create, and I'm just going to create a new tab here, a new page rather, and say I want to create a UML artifact, right? So I'll scroll down to the stencil that has UML 2.5 or 2.5, and what you notice here is that an object. If I can find what I'm looking for here, this is it, the one, the lifeline, right? When I pull a lifeline here, it's the object and it's an object name together with the lifeline here, this dashed line. Okay. Anyway, so we discussed this. Syntax is very important. It's very important because people will only be able to understand the things we've put together if you are following the rules. But also if you are leveraging model-driven development, for instance, syntax becomes extremely important. Something we discussed as well is the so-called activation bar, right? And the activation bar is a narrow vertical rectangle over the lifeline. And in essence, what this thing does is it showcases the extent towards which this object is active. Now, you notice here, right, from these lifelines, these lifelines, if you look at the actor lifeline, not lifeline really, the actor activation, it's much, much larger than digital object and metadata. What we are saying here is the amount of the time within which the metadata object is active here is much smaller when compared to digital object. This is what this means here. The size, right, of this rectangular bar. Hopefully this is making sense. We are essentially just showcasing the period within which this thing is going to be executing. Something else we realized was that time, right? Time is taken into account by looking at the methods that are being invoked. And incidentally, the passage of time is top down, is it? So time 0 is on the top left corner, 0,0 is top left. And as the objects are interacting with the passage of time, you notice that different sort of methods will be evoked, right? So the methods that are at the far top there are evoked much, much earlier than the ones that are on the bottom here. This is what this means. Now, we ended at a time when we were about to start our discussion of messages. We did highlight that a message is typically represented by an arrow, a different sort of arrows here. It's an arrow and the associated message name with arguments, right? So meaning that what we have here is not really a comprehensive sequence diagram, is it? Because we are not specifying the arguments for the methods. The way you specify the arguments is similar to what you do when you are creating your class diagrams, is it? So if there's a message associated with, so in this particular case, we have two lifelines. Let's say we have the class student, anonymous class code student, and then we also have course. And we want to model the fact that a student is going to be interacting with a course. I mean, at some point, obviously, you have a few other things here, but a student is interacting with a course. We know that one of the very first things a student is going to do is maybe the student is going to, I don't know if we can find the actual messages here, but realization. Yeah, sometimes these tools, right, when you lump everything together, it becomes a bit of a problem here. Message. So I have something like this, and what we can do is we can say well, a student, one of the things a student is going to do is a student will first of all maybe check, right? Check course. This is a method, is it? Check course or read course info or something like that. Now, if you think about course info, right? For you to read a course info, remember there are different courses. I'm making things up here, but remember there are different courses you're enrolled into. 30-20, 30-10. So meaning that maybe one of the arguments you're going to have to provide this thing is course ID. Right? So you're saying if we're building a piece of software where we'll have like an object student or a class student and a class course, at some point we know that the student is going to have to read a course or something like that. Right? And then maybe at some point this I don't know if maybe we'll have a course database, but at some point maybe the course class is going to return a message or something, and then again the student will pass another method to say, I want to, because you just don't, especially for your electives, is it? If you have electives at third year, you just don't enroll into a course. First, you look up information about the course. Maybe you have something like enroll course, like this. And again, you have course ID. The point I want to put across here is that when you're specifying these method invocations, the correct way of doing this is you have a method name and you specify the arguments. Now, the example I'm giving here is trivial. It assumes that these methods taken or they're defined using a single parameter, which is why we're passing them a single argument. But in actual fact, you could have a situation where you have a method that takes in a number of arguments, more than one, in other words. In fact, it could be methods that, like in this particular case, maybe in fact, you wouldn't do this. One of the things you would do is you'd say, as a student, one of the very first things I'm going to do is I'm going to say, list, assuming SIS was working like this, list all courses, right? It's like list all courses or something. And if you're listing all courses, you probably don't need to feed it an argument, although you'd say, oh, maybe you want to feed it a year or something, but or maybe the program or something like that. But list all courses, and then this method is going to list all the courses. And then once you list the courses, you then click on a particular course you're interested in, and then that ID of the course is going to be fed as an argument to this method read course info, right? And then you enroll into the course or something like that. The point I'm trying to put across here is that method calls or method invocations are supposed to be done in a certain systematic manner or way, if you will. All right. Anyhow, now it turns out, right, and this is important, it turns out that there are different types of methods, right? The one that we've been looking at, the solid line here, is probably the most common method, right? In fact, if we go back to something we pulled from your text here, most of these, if you notice, these are normal methods, synchronous methods here, right? If you notice the solid lines here. It turns out that the different types of methods, we have, I don't know if there's a discussion here. So you have invocation method messages, return messages, not methods, self messages, and destroy messages, right? So the type of arrow will indicate the type of message you're dealing with. With a normal invocation message, where you are calling, invocation is like you are calling a message in a different class, or we are calling a method in a class, because you can call a method from within the same class, right? It's possible, self-invocation. Well, it turns out that with an invocation message, what you do is you use a solid line, and what you are specifying there is a synchronous message, right? Where you're making a request and you're waiting for a response. So take note of the syntax, right? Yeah. You also have so-called return messages. And the idea behind the return message is simple. You are indicating the result. An invocation method is you are sending an instruction. I want you to do this, right? So if we go back here, in this particular case, this actor is saying, patient info. I want you to call this method view info. This is what I want you to do. Whereas a dashed line represents a return message. And typically when you invoke a method, usually when you're interacting with systems, when objects are interacting, there's usually feedback that comes your way. That's a return message, right? So a return message is indicated by a dashed line, right? So everything with a dashed line here is a return message. Okay, you are returning a result of something. You see this example here. I was saying when a user, a postgraduate student, is looking at ingesting a digital object, what they'll first of all do is conduct an invocation. We are calling this method from digital object to say deposit digital object, and then this object here there'll be a cascade effect. It will evoke another message in metadata called specify object metadata. At the same time, it will evoke a message called upload bitstream metadata in the bitstream class. These are all solid lines, right? After all of this is done, this bitstream class is the one that confirms the upload. It's a return message because of the dashed line here. In essence, it's sending a signal back to this digital object class to say the upload has been done. Now, when this bitstream class sends a return message to a digital object class, there's a cascade effect. There's another return message from the digital object class going back to the user to say, oh, your ingestion or your upload has been successful. It's confirmed. Do you understand this? So you have your invocation message, your return message. You also have a so-called self message. Now, the idea behind a self message is simple. It's like a message is being sent to the same lifeline. You notice in all of these different examples we have here, right? The lines are originating from one lifeline going to the next. If you notice, from this postgraduate to digital object for this, from digital object to metadata for this, from digital object to bitstream for this, from bitstream to digital object for this. But it's possible for you to have a self message where you are sending that message the same line. I don't know if I have an example here. Wow. I don't have an example, but you essentially, if you see this, no bitstream. It's originating from digital object and also terminating back to digital object. This is a self message. Okay? Anyways, and then you have a so-called destroy message. A destroy message, right? Where you're showcasing an object deletion. You typically would mark a cross, right, at the end of the lifeline. And again, I don't think I have this is the thing here. I don't think I have an example here, but you'd mark it with a I'll update these things, showcase how you specify a destroy message, but you mark it with just an X here on the lifeline. So if this was a destroy message, it would be an X on the lifeline right after this. Okay, so I mean, there could be other, at a bare minimum this should be sufficient. I think we've exhausted all the messages here. I guess we should be done here. Yep. So these are the messages, right? So the next time you see a diagram like this, you already know here that the deposit ETD is a what? It's a message invocation, right? It's an invocation message. So is specify metadata. So is upload bitstream. So is confirm upload, or they should have been dashed. And then the no bitstream is a self message because it originates from the same object and terminates from on the same object as well. Anyways, there are also so-called combined fragments, and this should be exciting for you. If you look at what I've been showcasing so far, like this, you'll be sitting there and you're thinking as a programmer, right? You're thinking, but if these things are happening as code is executing, code comprises of certain constructs, is it like loops and conditions or something? Well, the way you represent those things in your interaction diagram, your sequence diagram, is you use what are called fragments. Combined fragments are called. Combined fragments will allow you to represent or model control structures like conditions and loops, for instance. Okay, so the syntax is simple here. You specify a combined fragment using a rectangle, right, within your sequence diagram, a rectangle with the name of the fragment in the top left corner. So notice here, alt is an alternative fragment. Let's see if we have some on the thing here. Another alternative fragment here, right? But there are other kind of like fragments, right? Operators you can use like opt for optional fragments, right? If you have a condition, for instance, like true or false or something, if else kind of, or a looping fragment, for instance. There's more stuff, but I mean, you can have a fragment that will indicate parallel execution and breaks and all those things, right? If you remember your break statements in Java or something like that, right? So a number of combined fragments can be used. They're represented as a box or a frame, which encloses a portion where that particular interaction is taking place. The operator, the actual action being performed, is in the top left corner, right? And the types here, these are the types that are there, right? Alternative, optional, opt. Syntax is important, right? Opt is short for alternative, if else. Opt is optional, where you have like if the condition is true, right? You do this, else it's false or something like that. You can use option, opt. And then you have the loop. You know what this is here. You're performing some sort of iteration or something, right? And typically when you have like a loop operation here, a guard will specify the loop condition or the iteration count or something. In other words, you'd have, instead of ought, you'd have something like this. You know how you have ought? For loop, you'd have something like this with a guard. Say I is less than maybe 10 or something. What? I is equal to less than 10. So that you're trying to showcase that this action, like the method, is going to continue being called, for instance, 10 times. Yeah? If that makes sense. Anyways, so fragments can also be combined here, like you can combine loops and alternative fragments or something like that. So again, just to put it into perspective here, ought is like alternative, right? Where one condition, like one with a condition true, will execute ideally. Okay, and then the optional fragment here executes only if the condition is true. So in other words, if you have the opt here, you're saying that fragment is only going to be performed if the condition is true, if it's true. And you notice, if you're sitting there and you're wondering, how is this happening? It's like when you're invoking, when objects are interacting and messages are being invoked, the state of the system changes. Imagine you are a student and there's a login object. You log in. If your login credentials are true, the state is going to be different for when your login credentials are incorrect. So the behavior of the system changes based on the messages that are being passed, in essence. Okay? And then the looping fragment will essentially just execute multiple times here, right? And the multiple times is indicated by the guard, is it? Okay? Just an example, right? We have an alternative fragment, yeah? If else, you notice here the way we're specifying it, right? If true, the stuff that is at the top here is what is going to be executed. Else, right? What is at the bottom is going to be executed. In other words, what this is showing us is that when we're depositing an ETD object, we'll have to specify metadata, right? And then, once we specify the metadata, if a PDF document or Word document exists, right? Alternative, there are two alternatives here. If it exists, then we'll upload it, and then we'll have a confirmation of the upload. Else, that is, if the PDF document or Word document does not exist, then what is going to be executed is, after you specify metadata, there's going to be a self message to this digital object to say no bitstream, and then you're done. Alternatives. Now, I thought now would be a good enough time as any for us to look at some realistic scenario here, right? So that we understand what's going on here. Look at this. So this is our complete, and I have to apologize, ladies and gentlemen. This is not syntactically correct. Yes, Lighton knows that this is not syntactically correct because the interaction name is missing, right? There's nothing in the top left corner. I think when I was cropping this, I removed it. So at the top here is supposed to be something like SD and the interaction name here. Digital object ingestion workflow, something like that. So the idea here is, this is an actor, postgraduate student. By the way, this is an alternative way of representing an actor. You can use a stick figure, or you can still use the rectangle, but the name in there is not going to be specified similar to objects, right? You notice how objects can be anonymous here, followed by the class name, right? It's an anonymous object. Or you can specify the name of the object and the class name, right? For the actor, you notice here, we have the actor name followed by an annotation here, is Gulams, with the word actor to signal to say this is an actor, it's not an object, inscribed inside the rectangle or the rectangular shape. Yeah. So what's happening here is, if we are to understand this interaction, is a user probably is using a graphical user interface, right? They click on a link to deposit a new object. When they do that, they're evoking the deposit etd method, which is defined in digital object. Yeah. Apologies that the arguments are not specified here, but this is for simplicity's sake. Otherwise, people would be confused here. Now, you notice here that this is an evocation message, right? Deposit etd. When this method is evoked in digital object, once this is executed, there's a cascade effect. This digital object is going to evoke the method in metadata, code specify metadata. In other words, what's happening here is, it's almost like you have something like digital object do is equal to new digital object. We don't know the sort of constructor we're working with, but we're going to assume it's like this. And then you also have something like metadata md is equal to new metadata, like this. Something else you have is a bit stream. bt is equal to new bit stream. Of course, these things will be, because these are constructors, is it? In your code, this is what you'd be doing, right? Because these are constructors, they could probably have arguments, right? But we're simplifying things here. Now, what we're saying is that this deposit etd, it's like the postgraduate student, when they click a link somewhere, they're evoking deposit etd. So you're going to have a situation where the evocations here, you have do dot deposit etd, like this, right? When this is evoked, at some point you have something like md dot specify metadata, like this. And then what else? Afterwards, you have a condition, right? So it's almost like in your code, you're going to, if you're looking at kind of like implementing this in code, you have something like if the bit stream exists. So if bit stream exists, you have something like this. If bit stream exists, what do? You're invoking upload bitstream in the bitstream object. Bitstream object is bt, so it'll be like bt dot upload bitstream. And again, we're not providing arguments, but in this particular case, maybe the path to the file or something like that. What else do? You then have, in this same if condition, right? You have, this is supposed to be a return message, but that's fine also. There's a method that is evoked by bitstream, which is in digital object. So you have something like do dot confirm upload, like so, right? And then, because this is an alternative fragment, it's an if else. You say else this. Else, you are evoking in digital object, you're going to invoke no bitstream. You understand? And you see, what I'm showcasing to you right now, right, is precisely why we are creating these different views. So it's like if you give this to a programmer, I'm not even a professional programmer here. I don't do this on a daily basis. But just by looking at this, I know exactly how to write code. Imagine a situation where I just told you to say, look at this. I just told you to say, I have this use case diagram where I have an actor called postgraduate student who interacts with a use case called ingest digital object. This. I mean, think about this for a second, right? It's like you have to second guess what is happening here. It's like, so how does this interaction actually happen? How does this postgraduate student, what happens when the postgraduate student is performing the task in this ingest digital object? A use case is not sufficient for you to write software. You end up making errors, right? But if you have information like this, you can easily translate this into code. You notice this? Very easy. I'm ready to, please, before you start telling me, no, Lighton, you're able to do this because you, Lighton, are the one who created you're the one who created the sequence diagram, so you know. Well, I guess. But really, I'm just translating what I'm seeing here. In fact, I'm even able to notice that there's some mistakes or something like that. Anyways, so we are saying here, like if you're trying to understand what's going on here, the user clicks on a link to deposit a new digital object. And then the digital object is going to be activated for depositing an object, right? Deposit ETD. Digital object activates form to deposit an ETD. The digital object activates form for uploading metadata here. It shouldn't be bitstream here, but metadata. And then the digital object then activates the form for uploading a bitstream. And then the bitstream confirms the upload. This is a first case. I should have, I do apologize. I will have to reweight these things. This is 1. This 2 is supposed to be metadata. And then this is supposed to be 3A, which is upload bitstream. 3B, confirm upload. Right? And then we have 4A, which is going to be no bitstream or something like that, an alternative. Like that. Anyways, so you notice that it's quite easy to kind of like understand this. Is this making sense? I'm looking at the time here, and before we start, we have a class tomorrow, right? I think it's at 12 hours, I think. I don't know what we agreed with the madam here. But before we transition to activity diagrams, I thought maybe I would pause here and just ask people if you understand this. Or if you have any specific questions anyway about how we create sequence diagrams. The key thing here is with sequence diagrams, you are expanding upon your use case diagrams, and some of the key concepts covered include, or the key elements are things like your lifeline, activation bar, the different sort of messages, combined fragments. Do you understand this? It's been there, right? We've had questions. Tell us what's happening here. Just explain to us what is happening here. Failing. Or draw a sequence diagram that explains this sequence of events. Do you guys understand this? Are there any questions? Okay. Yeah, critical thinking skills. Anyways, it's going to be a short class here. You don't have to make this any more painful than it already is. I was tempted to continue this discussion so that we start looking at behavioral models. But I'm just going to introduce this, and then when we meet tomorrow, I will liaise with Muna and Violet, so that we agree on a time. But But yeah, on the time here. But it turns out that our next discussion is going to be on behavioral models. And the idea behind behavioral models is simple here, right? They'll allow you to represent the dynamic behavior of the system as it is executing. So they will show what happens or what is supposed to happen when the system responds to a stimuli. Like I've logged in. What happens when I log in, for instance? It's like when I log in, there are two possible paths. And I know some of these things, you say, well, you can represent this with a sequence diagram, but you will see when we start looking at activity diagrams that the notation makes it a lot easier for you to understand how the system behaves, right? So they'll show you what happens when a system responds to a stimulus, right, from the environment. So the stimulus could be, for instance, what happens when data is being processed by the system, or what happens when a specific trigger happens when somebody logs in, for instance. Well, when somebody logs in, we have two possible paths. This person is going to specify the username and the password. When these things are correct, then they will be redirected to a dashboard. It's like what happens when you are here, right? When you're on the Moodle or something like that, you log into the Moodle or something like that. It's like, I'm on the Moodle right now. Okay, I guess I'm going to log out here. I'm on the Moodle, right? Two things can happen. Well, two possible outcomes here. I'll be able to log in, or the login will be invalid. In fact, if you think about this, right, there are a number of possible options. Two main possible options here. You can either log in or you fail to log in. But for you to log in, right, for you to log in, you must provide a valid username. If I just say LPiri here, right, and try and log in, well, I'm still getting invalid login. But in some systems, it will be non-existent username or something like that, right? So what your activity diagram, what your behavioral model does is it showcases what actually happens, right, as data is being processed. So I will showcase things like this. It's not complete here, but yeah, I'll have to make sure we have a more comprehensive example here. I think it's a time when we're going to be latching on to these other things, right? Like external artifacts we've created using draw.io or something like that. But you can represent control flow, for instance, or you can model what happens when there's a decision being performed and all those things. Anyways, so we're going to discuss this tomorrow. I see there are no questions from you people. I'll see you tomorrow then. I just wanted to, this tomorrow thing here, I wanted to suggest to Violet and Milna here to say we have an interaction at 12. 12 would be good because I normally have a meeting at 13, so 12 would be good. Yeah, but I'll have them confirm, or I'll confirm with them or something. But tentatively, it's 12. Okay, and then also, just brace yourselves. Somebody's saying, what of Sunday here? Unfortunately, Sunday is a bit tricky for me. I have another class scheduled for Sunday. I have other classes and interactions scheduled for Sunday. But I'll chat to them and then we can find out if you guys would be okay with a slot on Sunday. That's possible as well. The thing I wanted to mention is that this coming Thursday, we're going to have, we're supposed to have presentations of your SRS documents. So you want to prepare those things. You're going to walk us through what it is you did, right, to put together SRS documents or something like that. All right. With that being said, thank you very much, everybody. I will see you hopefully tomorrow or Sunday, as Miss Mbozi has stated. I'm sure she's an Adventist or something. Thank you very much and enjoy your Friday.